Hello, I just want to show like a basic introduction to my new project that I'm working on over my isolation period. It's a new CNC machine to replace my old one. Um, just one thing to note: there's a few bits missing from the model here, like the the cable tracks and nuts and bolts. But I've got the important stuff. Um, I'll try to record a lot of the process of me making it. I'm already sort of halfway through making it as I speak. I've got a lot of time-lapse footage, but I'll also be taking real-time documentary like style video. Um, First, I'll talk about the desired functionality that I wanted in a new machine. Um, Firstly, I want it to be a bifunctional machine, so it can do routing and plasma cutting. Um, Another desire I wanted was for it to cut a larger area, like a larger work area. Um, my other machine has a 600 by 1200 millimeter work area, which is pretty good. That's actually very handy. But this one should be able to handle a 1200 by 2400 millimeter sheet. Just main reason for that is I want to try making some of those like garden fencing, house fencing, not fencing screens, those beauty screens you see. Um, so another functionality I want is sort of uh, deep, um, a deep Z-axis for like foam carving and such, and using a 5-axis head on the end of this. I'll show you a bit more of that later, but this is capable of doing that with a little bit of change in the future. Um, Another ability, I want it to machine metals and plastics better than my older machine. I'll talk about all this and where the old machine fails and how this one should be better. I want this machine to be more precise than the old machine. That's a pretty given. My old machine was sort of thrown together real quickly. I didn't really, I obviously measured lots of things, but I didn't use precision techniques, precision measuring instruments, and so on. Another thing that I want the new machine to have is trustworthiness. I don't mean trustworthy as if it's going to run off with your money or anything like that, but my old machine, um, like repeatability on it's fine. Repeatability on this should be fine as well. But on the old machine, when you do a cut, it wasn't always exactly the size. And that's not necessarily a failing in me setting up the steps per millimeter and so on. I think it's just a little bit of uh, flex in the gantry means certain cuts will uh, deflect a little bit, certain depth of cut will deflect a little bit, and so on. So that's something I'm tackling with this new design. Uh, I do want the new design to be more crash resistant, more jam resistant. I'll tell you more about that later. So that's the functionality I want the new machine to have. Alright, so now I want to talk to you about um, the choices I've made and the reasons for those choices, and I'll show you a bit more in detail about this machine and my reasoning behind things. So the choices I've made, the first choice is to go with a full computer-aided design method for designing this. That means obviously modeling it up. The modeling helps me um, run through actual motion of all these axes, and I can make sure nothing is colliding. Uh, that's something hard to do on paper, but when you can visualize it and you can run collision detection, wherever it is, inspection, uh, interference, sorry, whatever. It shows you where things collide, and of course you can just do it by eye while moving things. that's a helpful process with CAD. Another thing is the simulation. I can test the material strengths in a simulation. I can see where rigidity is failing or where rigidity is unnecessary, and I can tack onto it as needed and follow that process of design, iteratively. So this is sort of my latest simulation of the gantry. It looks a bit like spaghetti. That's just because you have uh, an exaggeration essentially, so you can helps you visualize what's going on. So the worst uh, displacement you're going to get on any gantry machine is the gantry itself twisting. So a force pushing this way. So my force is set to like 100 newtons or 1 kilonewton, which is equal to about 100 kilograms of force. And you can see with that amount of force, I'm getting like 0.1 millimeter of deflection at the very end here. This simulation model, like everything's, the key structural member here is to scale and the different materials and so on. But like the spindle motor is, I've only modeled it in to get the weight and not the exact dimension. Same for the stepper motors at the back here. They're just modeled to get the weight in because I don't need the full geometry of the motors and so on. It just adds more complexity that slows down the simulation. It's not needed. All I want to do is simulate the weight and the rough placement of that weight. And things like hanging the motors on the backside sort of helps distribute the weight. So you got relatively equal weight pulling down here and a relatively equal weight pulling down here because of the spindle and the z-axis plates and such. So that stops a asymmetrical force from rotating your gantry unnecessarily. Like gravity is that asymmetrical force. If you've got too much weight on one side, it's going to give you a lever action and it's going to twist your gantry, and it's going to give you unwanted, not only is it going to give you downward displacement, it's going to give you a displacement in your whichever direction it's twisting, whichever direction it's torquing. Here's the other load case with a force pushing, in parallel with the gantry essentially, and you can see it's far lower. Actually, that deformation is the deflection, whatever, displacement, whatever, is the stepper motor, not the actual spindle end. So there we go. Now the spindle end is represented about 0.037 millimeters. So that's really good for 100 kilograms of force, which once again, it's not going to really experience that amount of force. So that's the big benefits of the computer-aided design for helping me make this. Alright, another choice I made is I've decided to go with closed loop stepper motors. Not because I'm afraid of losing steps. The current stepper motors on my old CNC machine, they never lose steps or anything like that. Only if there's like a catastrophic crash. But you don't worry about that. The main reason why I want the closed loop is that the controller will send out an alarm signal if it detects that your actual step count or your actual revolution count isn't matching the signal input it's getting. So if it gets too out of whack, it'll just shut itself down and give a error signal. And I'm going to wire that into the controller so that it just shuts down the whole machine. So essentially, if this thing has crashed, which is why you would miss your steps pretty much, it'll turn off everything, which is ideally what you want. Whereas with my current machine, it doesn't do that. If it crashes, it'll keep on moving the other 3 axes, or worst case scenario, one of the gantry motors will stop and the other one will keep running. So you'll end up with a nasty twist in your gantry as you have an asymmetrical force driving it. And the closed loop stepper motors should let me get higher speed too. So that's my main reasons for using the closed loop steppers. Alright, another choice is rack and pinion. I've decided to go with rack and pinion over ball screw or belts. I initially considered belts, but then I decided against it because it doesn't make sense to go with the belts, which is going to introduce a little bit of elasticity when I'm designing a fairly rigid machine to begin with. It made sense for like a 3D printer or a laser cutter or a only plasma only cutter, but for something which does your milling or routing, should I say, it doesn't make so much sense if you want that accuracy and dedicated rigidity. Rack and pinion, the reason why I've gone with that over ball screws is the length of this travel here is like 3 meters. 3 meter long ball screw is going to start whipping, I am sure of that. So my only real option is a rack and pinion. My next choice I made was to go with the HG 25 linear rails. That just means it's 25 millimeter rail. HG is like a standard load rating and so on. Let me show you a bit. So these are the linear rails I had on my first machine. They've got like a supported cylindrical hardened shaft, and you have recirculating bearings running up and down it. They're very noisy. The preload on them is pretty dodgy, and their profile is fairly big, and I'm pretty sure they'll leave grooves in your shaft here after a while. And of course they allow rotation along that axis because they're circular, whereas your sort of boxed way linear slides, they limit all rotation. They're a lot quieter because you have far less bull racer channels, if that's the correct term. There's only 4 of them, 4 channels, and it's a lower profile. It handles preload better. Well, not handles preload better. It actually has a preload to begin with. You can specify whatever preload you want. You can have real heavy, or you can have pretty much none. So yeah, that's my reason for choosing the linear rails. Alright, my next choice I've made is it's the basic frame design. So, well, first I'll talk about the frame materials. So I've chosen to pretty much have all steel for the table base and almost all aluminium for the gantry itself, with the excluding the small steel hollow sections I have on either side for a bit of rigidity. And of course, like the spindle itself is going to be steel, and the stepper motors are steel, and the rails, I can't do anything about that. But my reason for using steel on the base is it's heavier, it's more rigid, it's cheaper, it has better vibration dampening, or has lower resonance. So it's a no-brainer to use that. It's easier to weld, easier to work with. My reason for using aluminium for the gantry portion, the moving portion, is it's lighter primarily. I can get a more rigid setup for a lighter weight structure by using aluminium, as long as I think about it properly. There's like the whole simulation process has shown me where a lot of like for instance, I have little stiffening brackets embedded in this hollow tube, and that increases the rigidity, it stops the twisting action on that gantry a lot. And just things like, as I said before, the weight placement on things, seeing how thick of a plate you truly need to get a certain amount of rigidity. It's all helped me design this with the lower rigidity material. Alright, now I'll talk about the choices I made for the actual frame design. So these sort of rails here, these span across to form your table base essentially. Something either like a MDF sheet or a plywood sheet goes on top of that, and that's your fixturing surface. Or you can put an aluminium T-slot plates or something like that in. Either way, all these tubes are going to be just bolted on to this primary rail, which holds the X-axis linear slide and the rack and pinion. So you can unbolt this table section essentially, and you can lower it and bolt it onto this section. Yeah, if I can select the surfaces right, but you get the picture. So it gets lowered, and if you notice in the design, there's no intruding crossbars or anything on the inside. It's all hollow. So this can be a work area, so you can get that nice Z depth that you can put literally whole stumps of wood if you want to machine that, or carve out foam. So that's one reason why I sort of had this detachable table section. Another design feature obviously is it's a traveling gantry style machine. That's just pretty much the most common way to do a big format router. That's how they're all done. I'm not sure what other styles. There's fixed gantry, where the table itself slides in and out, and your gantry is fixed in your Z and Y travel up and down on your gantry. But that's a bit silly for my needs here. So another feature is the Z-axis is actually detachable. That's another reason for choosing rack and pinion, is the rack can just slide right off the pinion. It's not held in any way like a ball screw. So you can just slide this whole thing off and put on a more extended Z-axis, which lets you get all the way down. That's what my long boy simulation here was for, just to see how bad it will get, and it's not too bad. This is not with a 100 kilogram force, this is with a 10 kilogram force, or about 100 newtons, which is more realistically what you'll experience if you're machining wood, and foam is going to provide you with no resistance pretty much. So my next choice that I've made is to use a 2.2 kilowatt water-cooled spindle. My main reason for that is I can cool it at a lower speed, like a lower RPM. My old CNC machine, it has an air-cooled spindle, and the actual fan motor is literally driven off the shaft of the spindle itself. It's not a separately powered fan. The failing of that is if you run the motor speed lower for cutting metal or for cutting plastics, because if you cut plastic at too fast of a speed, it'll just melt. Same for aluminium, it'll just melt onto your cutter bit, and instead of actually cutting, you'll just be doing a friction cut. But because that speed slows down, the fan slows down, and you get less cooling. And of course, another failing of those spindles is the slower they go, the more current they have to push through it to compensate, to keep the torque up. And of course, that creates more heat. So you're in this stupid loop of making more heat, but giving yourself less cooling. But water cooling eliminates that because your water controlled loop is completely separate to the spindle speed itself. Another benefit is obviously that 2.2 kilowatt spindles have a bigger collet, so I can use bigger bits. I have a lot of 12 millimeter bits or half-inch bits, and that will allow me to use them on this machine, whereas currently I only have them for a little handheld router. And of course I can buy more bits for it. I have a wider range that I can use when I can now use 12 millimeter diameter bits. And of course the extra power in the motor will be handy for cutting metal or for really ripping through wooden sheets. Another choice I've made is the variable frequency drive control for the spindle. I'm using a 12 amp one, which is technically a bit overpowered, but as I've said, the water cooled spindle, I can suck out a lot of that heat through that water cooling, so I can overdrive that spindle a bit if I really need to. But another benefit of the VFD that I've chosen is it has like your overcurrent protection. So if the spindle ever stalls, because you come across more material than you expected, or if it just jams up for whatever reason, too much load, it will also send out another alarm signal just like the stepper motors will if they stall. And I'm going to tie that into the same emergency stop function that will just stop the whole machine. So it stops unwanted damage from occurring by stopping all movement as soon as possible and turning everything off. Another choice I made is to use linuxcnc. I use Max 3 on my old machine. Max 3 is fine. It's pretty customizable, it's fairly powerful. But with linuxcnc, I like the idea of just using Linux instead of Windows. Linux is it's a smaller, simpler, cleaner operating system. It makes more sense for an industrial machine where it's dedicated to doing that and not being a general computer. Another thing I like about linuxcnc is it's fully customizable in that it's like open. I think it's open source. Don't quote me on that, but I'm pretty sure it is. So you can change anything at all. Whereas Mac 3, you're limited to changing the UI within limits of their arrangement tool and scripting buttons and the brain script interface, I think. It's still highly customizable, but nowhere near as much as an open source program. It's free, so that's another benefit to it. And I like the abstraction system linuxcnc uses to separate the software and the hardware interface. Alright, my next choice is to use a Mesa card to control the motion. So they're not super expensive, they're not super cheap. It's a pretty clean, simple card. It's got everything you want. Yeah, 48 general I/O, like input-output connections. It has a 16, not 6, 5 axis control, like high speed control too. You have like a high speed, what's it called? So a high speed encoder interface for your spindle. So another thing you could do is track the spindle using the software, and if the spindle stops when you don't expect it to, you could do the shutdown. Or the primary function for it is you can do tapping, because it lets you control the motion in regards to the spindle's speed. And it just has so many other functions, like you have manual pulse generator inputs and all your isolated isolated controls and your high voltage signal capability, so you can um, you know run a higher voltage for your switching and gear and stuff to get rid of unwanted noise, or essentially you're talking over unwanted noise. I think it has analog inputs as well. And it has like an analog output for controlling the spindle via the VFD, and like serial capability. Like you can add expansion cards to this to add even more functionality to it. It's just sort of a no-brainer to use these cards with linuxcnc. They are literally made for each other. So yeah, that's my reason for using the Mesa cards. My last choice I've made is the modular use of space. So because it's got such a large area in general, not only can I cut a big panel, I can split it in half. I can use one half for general mounting of sheets, which is probably what I'll be doing most of the time, and stick with the other half having a water table for plasma cutting in it. And the water table can just sit in there, and I can just drain it and then lift the table out when I want the whole thing accessible. And there's this little sort of portion at the front here where the whole system overhangs a bit. So if I'm trying to machine something that is a bit awkward to hold, I can mount it along this on a side plate here, for instance. I'm just going to sort of have a modular mounting system at the front here, so I can attach plates like this, or I can attach these big rigid backs here and hang a T-slot plate here, or vices or whatever. Just a more modular setup with nothing in the way. Um, you know, and as I said, this big open space here, I can put like a fourth axis rotary axis in here and machine like whole columns or decent sized statues. I have that ability and that freedom because I have this envelope to work with and a fair bit of rigidity to make use of it. So that's everything for my choices that I can think of, at least. I'll talk to you about choices that I have yet to make, or that I need to do a bit more research up on them. That is what plasma cutter I should actually use. I've seen people suggest the Lotus. It's fairly cheap. I don't know if it's a Chinese made thing or if it's American. Sounds Chinese. And I'm not quite sure what torch head to use either. I'm not a plasma expert. I've never actually used a plasma cutter torch before. But I've done a fair bit been looking up a lot on it, and like key modules I want for controlling stuff like torch height control, which is something that sort of hijacks fine motions of the Z axis to make sure your height from your workpiece and your nozzle is adjusted to keep an optimal plasma arc, I guess. And you need to monitor the arc voltage. I'm not quite sure how you do that, if that's something that the machine does, or if there's a tap that you can use to detect that. As I said, I'm just not quite sure on the plasma side, but I know that the key fundamentals is your machine has to be able to move quick for the most part, and this machine will be capable of moving quick because of these big motors and the gear ratios I've got on them. They can handle that acceleration. I think they should be able to handle easily over a G of acceleration, and these motors should be able to safely handle 4,000 millimeters a minute, which is 40 meters a minute, which is fast enough for any plasma cutting, I'm pretty sure. You'll never use that for routing though. That'll be rapid movement only for routing, which is a big time saver. Another choice I have yet to make is the cutter bits themselves. I haven't delved too much into the cutter side. I've just sort of used generic cutters. I've experimented like with single flute cutters, two flute cutters. I don't think I've used any 3 flute cutters or 4 flute. I think I used a 4 flute cutter once, but it just turned out horrible. I never use it again. Most of the cutters I go for are carbide. I've got some high-speed steel ones just for wood cutting, but I've used high-speed steel before on trying to cut aluminium, but it just melts too much. It's not smooth enough, essentially, so it just picks up aluminium too easily. I want to try experimenting with like highly polished cutter bits for aluminium cutting, and to get like the right flute angle to get better chip evacuation and such. Another thing I want to try is like a basic mist coolant system on this. Make it easier to cut aluminium. I do want to cut steel at some stage, but this machine is not going to be optimized for steel. It's just optimized for aluminium. Another thing I've yet to decide is what I'm actually going to use for the bulk table here. You've got these underlying ribs. They provide your support that you mount something to. But I'm not sure if I should just use a big MDF sheet on it, or if I should use plywood, or if I should buy some aluminium extrusions, T-slot extrusions, and use those to make the table. That's what I have in my current CNC machine, and it is wonderful to have that T-slot set up in the hard, rigid base. But I find myself most of the time just putting a sheet of plywood over that, because I would never cut anything directly on the aluminium base plate if my cut is going to be going through what I'm working. I have to have a sacrificial layer, or I have to jack up my workpiece so there's clearance between the bottom of the workpiece and the table. That's pretty much everything. This machine is currently naked. It hasn't got like the dust covers and everything over it, or the bellows. Let me enable those and I'll show you what the machine sort of looks like in its final state. Alright, just waiting for it to load. There we go. So this is like with the coverings over it. So the major portion of the Z is sort of hidden underneath an extender there. So pretty much everything's covered. There's sides here, they're still exposed, but they have a cover over the top of them to stop stuff from directly falling down onto it. But if you get like a small breeze, it will blow stuff straight onto that rail. The rack here, I haven't modeled any teeth in, so it's just a bar at the moment, but that's all I need. It is upside down, so nothing's going to fall onto those teeth, because unless whatever it is defies gravity. But yeah, these rails, the top section of these rails might collect a little bit of stuff, but the cars we've gone out. But the cars that travel on them, they do have wipers to clean stuff off as they travel up and down. But I do want to keep as much stuff off the rails as possible. And the whole front here has a bellow system, so that protects the rails in there. But the rack back here is on its side. But I've got like a little foam or rubber flap over it, so that will stop pretty much most stuff from landing in that track. You can see like the tray here where the cable track will come out of. That's where it will feed into. So it will just loop through here and go down here and terminate about halfway. Not much to show about this really. It's just sort of basic sheet metal box structures that go over and make it easy to clean, makes it look nicer, and keeps dust out. This is sort of the look of it in its final state. I'm still not quite sure what to do with the front. I've got like the spindle mounted here and the plasma cutter. The plasma cutter is going to have an additional extender here, either a piston or something that pushes it down by compressed air, or another motorized axis to help push it. Because even though it's already mounted on this one axis, which is motorized and controlled, I would have to remove the spindle essentially, or move the spindle up at least to get it out of the way, or lower this if I want to do plasma cutting, and then change it back if I want to do routing. But it'd be nice if I can sort of automate it so I can use the spindle to drill holes, because plasma cutting is good for cutting out a contour, general contour, but not for cutting out real accurate hole sizes. That's where a drill might come in handy. And this spindle should be able to drill out things, especially if I get a auto tool changer for the spindle, which I want to do in the future. And what you do is you make a rack of tools along the side in like an enclosed box, and that will open up and the spindle will come down, suck it up. It'll deposit the current one into a slot, then lift up, then move over to where the other one is and go down and suck it up, and then your drawer will close. And you can do that pretty easily with linuxcnc. Just your amount of controls with that program, and the Mesa card is made for all that sort of stuff. But that's everything I have to show so far on my model. I'll hopefully start compiling together my actual videos of what I've been doing so far. I've finished most of the metal table, and I've done some of the aluminium gantry beams, and I've played around a lot with the motor and the spindles and the water cooling system. Yeah, that's all for now. Goodbye.